Hello, my name is Matthew Lichtenberg, and today I'll be presenting my work on AI for nanoscale imaging of contact in the human-machine interface. I would like to thank my mentors, Dr. Yuan Ma, Professor Cynthia Hiplo, as well as the program sponsors, the Invent Lab and the Texas A&M O-REU program. The core question that we're dealing with is, what does it actually mean to touch something? If your finger is too close to an object on a molecular level, there tend to be interatomic and molecular interactions which will form bonds, and so that's not what's really happening when you touch something, because when you touch a chair, your hand doesn't then stick and bond to the chair. Similarly, if your fingers are too far away from an object, there's no measurable interaction. So the question that we're really looking at is, what does it mean for surfaces to be in contact? Finding the true contact area is critical to understanding more advanced models of friction. The model of friction that most people watching this are probably familiar with is the Coulomb model, where frictional force is equal to the normal force times a coefficient of friction. This model assumes that the normal force is proportional to true contact area, which oftentimes just simply isn't the case. For example, think about a piece of tape stuck to the ceiling. In this case, there's actually a negative normal force pointing anti-parallel to the ceiling's normal vector, because any force countering gravity must be pointing into the ceiling. But you still don't have any kind of negative friction sliding the piece of tape around on any surface, ceiling or not. And that's because the Coulomb model begins to break down under scenarios like these. This is also the case for human fingers, where the relationship between the force you apply to a surface and the contact area isn't as simple as a linear relationship because of the nature of fingerprints and all of the ridges and peaks and valleys that exist on your fingerprints. For these examples, we can look at more advanced models of friction like the Hertzian model, which says that the frictional force is equal to the shear stress times the contact area. And this is a better model for modeling things like fingers, but it also has a variety of assumptions which aren't always the case. Here you can see a close-up of your finger ridges on your fingerprints. The dark spots correspond to nominal or apparent contact, which is the indication that there's something touching the surface, but it's unclear as to if that something is actual skin or just water or skin oil. One mildly annoying thing is that you can see these dark spots which don't move with the real darker spots, and those are not actual contact, but they probably have something to do with the background that is the glass that the image is being taken over. We can apply some video editing techniques to remove all of this background noise, including some of the yellow coloring, to get a much more precise image. We're also going to need some way for a computer to distinguish what is and is not a dark spot. So we can take this filter with the background removed and convert it all to a grayscale video. And then from there, what we can do is further binarize it into black and white. Which allows the computer to very easily detect the boundaries on what is and is not apparent contact. This is done by implementing the Moore neighborhood tracing algorithm. Here we can see the two types of contact in a little bit better detail. Here we have the images in their actual size as they would appear in a measurement, but we can zoom in to get a better view of them. We can see that in the true contact, there tends to be more of a wispy pattern, and it's more fractal, whereas the apparent contact tends to be rounded, because apparent contact comes from liquids, which have to maintain a surface tension, which is optimal with a spherical or hemispherical geometry. Further, because of the more wispy nature of true contact, you can see that there is a greater variation in the coloration across the sample, whereas tend to have a much smoother transition through colors within apparent contact. Here you can see three samples that would be difficult for a human to categorize. They're kind of round, but they're also somewhat elongated. They also have variation across color in some regions, but not others. And overall, it's very difficult to figure out what these are just by eyeballing them. This is where supervised machine learning comes in. In this method of machine learning, we use a large number of labeled samples and let the computer figure out what patterns there are and what makes an image look like liquid or skin. We do this by feeding the computer a ton of labeled examples, and the computer will sort through them and make its own connections. However, in order to do supervised machine learning, you need to have data labels. And this is because the computer needs to know what it's looking at when you feed it tons and tons of images. These data labels are not trivial to create or find either, because if we had an algorithm where we could feed the computer an image and create a data label, well, that's actually the algorithm that we're looking for. And so we can't use such an algorithm to create another algorithm. We can get around this, however, by analyzing samples of gloved fingers. When you put a glove on your finger and then measure it, you can be sure that there's no water or skin oil getting on the sensor's surface. Likewise, you can also wet the glove and be assured that all of the contact is going to be wet contact and there's just going to be water everywhere. This gives us our training labels and allows us to continue on to the neural network. The network architecture was fairly simple and consisted of a combination of convolutional layers and fully connected layers. I decided to keep the neural network architecture simple to prevent overfitting. However, despite the relative simplicity of this neural network, as you'll see, the accuracy was actually very good. Here you can see the results of the training process. Over many iterations and epochs, the accuracy of the neural network slowly approaches 100% and levels off at over 99%. Using this neural network, we can get our final results. The graph here shows the proportion of true and apparent contact over each frame of the video that I showed you earlier. On every frame of the video, we apply the neural net to every single spot, and the neural net will make a classification as to whether that spot is true or apparent contact. From this, we can see that on average, the true contact is 88.95% that of the apparent contact. There are several limitations of this work. The first is that the algorithm isn't particularly equipped to handle mixed contact, that is, where there's water surrounding a true contact. The algorithm right now can only classify contact as one or the other, and a mixture would be harder to do because it would require data labels identifying which parts of mixed contact are actually true, so we didn't have the capabilities to do that at this time. Additionally, we assumed that the true contact of a glove will look fairly similar to the true contact of skin, and there are several reasons to think that this is a fair assumption, but as all assumptions, it will have its limits, and it would be beneficial to obtain some type of data with Raman microscopy that might allow us to train on data from an actual finger. Lastly, the classification system was trained only on water and a wet glove, and it would be interesting to see how things change if we also trained it on a glove soaked in skin oil. Thank you for watching. Have a nice day.